on my channel. Okay, today we will continue with the physical process, energetic factors. In particular, we will introduce the models we may employ for describing the effects of solar radiation. We have already said that solar radiation is the main source of energy for the ecosystems. In particular, we mean the main source for a basic process of biological biomass production that is called primary production. So the solar radiation is the forcing function for many ecological processes, starting from photosynthesis, photolysis, methane evapotranspiration, and so on. We may start by introducing the definition of the energy transported by light, by this equation, this well-known equation. We may say that the energy transported by a photon is equal to Planck's constant h times the frequency of radiation, or the Planck constant h times the speed of light divided by the wavelength. We have already said that Earth's surface lowers the quality of energy, meaning that photons are absorbed in the visible range or in the ultraviolet range and retransmitted as heat in the infrared range. We have already seen with this schema, that is the energetic balance describing the fate of the energy coming from the sun and arriving at the surface of our planet. Just for a moment. In terms of different forms of solar energy, we may say that of 1,360 watt per square meters, what is the solar constant, at the intermediate distance Sun-Earth, this radiation may be subdivided into some different intervals. For example, 50% of this radiation is infrared, thermal radiation, meaning that it arrives on the surface of a planet in the interval 0.71 to 3 micrometer, and it is absorbed and reflected from CO2 and other gases in the troposphere. Just to recall you, these are the processes that generate the greenhouse effect. This radiation, this 1,360 radiation, 41% is visible radiation. So this is the radiation that is mainly responsible for the primary production. So this is energy converted by primary producers by the conversion of elementary elements like nitrogen, phosphorus, and so on, and converted into biomass or organic matter. Then the remaining 9%, that it is ultraviolet radiation, will be subdivided into these intervals. Of these, we know that 4% is absorbed and reflected in the stratosphere, while of the radiation, but it is in the visible range and in the close ultraviolet, 0.34 to 0.40 micrometers, 46% of this radiation reaches the Earth and is reflected after being used and degraded by ecosystems. This 46% refers exactly, it is this quantity of radiation that reaches the surface of the planet. Now, we have a problem of defining the currency by which we can measure these energies. The standard, this is a list of standard currencies by which we may measure the energy transported by radiations. The classical physical unit is watt per square meters, solar constant. And then here you have a list of conversion factors that allows you to convert from watts to square meters in BTU, Langlays, kilocalories, or calories, or megajoules. We have introduced a new interesting currency, that is the Einstein. The Einstein is 1 mole per square meter per second. 1 mole of what? 1 mole of photons per square meter per second. Of course, we cannot convert this currency into the other currencies because here we are just saying that 1 Einstein is made up by 1 mole of photons without saying anything about the type, the characteristics of the photons. And you know that photons, as we introduced here, depends, the energy transported by photons depends on the frequency of the light of the photons. So the interest in introducing this currency is that we can employ this currency to measure the energy arriving from the sun that may be used to produce photosynthesis. We employ the concept of photosynthetic active radiation, PAR, by saying that 9 moles of photons in the visible, so photons that may be employed for producing photosynthesis, are used to fix 1 mole of oxygen, that is a macroscopic chemical product of the photosynthetic process. Okay? How can we model the energy coming from the sun on the Earth? First of all, we shall recognize the fact that not all the places and not all the period of the year receives the same quantity of solar energy. In fact, the solar energy that reaches the surface of a planet depends on a quantity that is called the photoperiod. Photoperiod is a portion of the 24 hours daylight in which, the 24 hours day, in which we have solar irradiance or radiations coming from the sun arriving on the Earth. The photoperiod is function of the day, of the period of the year, and function of the latitude of the place. So it is made, the function describing the photoperiod is P as a function of day of the year N and of the latitude phi is equal to twice the arccosines of the tangent of the latitude times the tangent of the solar declination delta divided by 360. There is nothing particular new or special in this model. These are astronomical models. So these are models that, as a function of the movement of a planet around the sun, describes how it changes the quantity of solar light that arrives on the surface of the planet. Again, photoperiod depends on the day of the year and on the latitude. So on the time, season, day of the year, and on the place at which this energy arrives. Concerning the solar declination, what is the solar declination? Solar declination is the angle between the line linking Earth, Sun, and the equatorial plane. For the solar declination delta, we have this function as a function of the yearly angle, epsilon. So we may say that delta of the yearly angle epsilon is equal to this combination of sine and cosines. So this is a trigonometric function that is obtained by interpolation linked to the movement of the sun around, to the movement of the Earth around the sun. Then we shall explicitate a function describing the yearly angle. The yearly angle as a function of the day of the year n, we may say that the yearly angle epsilon of function of the day of the year n is equal to 360 multiplied to n, so the number of the day of the year minus 21 normalized by 365. N is started counted 1, n equal to 1 refers to the 1st of March of the year. Why do we make this model? Because we calculate the yearly angle as a function of the day of the year, and we start to count the day of the year on the 1st of March, and we employ this kind of model in order to account for leap years. And you know that leap years are years in which we have 360 days. So this is why, 366 days. This is why we have this normalization function. We subtract 21 to n, where n is equal to 1 corresponding to the 1st of March, because the 21 of March, it is the summer equinox. So this is the day of the year in which we have the same duration of light and dark. So it is the equinox. Then, by making some consideration on the quantities that appear on the photoperiod, for example, we may calculate the tangent of latitude, maximum latitude times the tangent of the maximum solar declination. This quantity is always smaller than 1. Why this? Because of the maximum solar declination is 23.5 degrees. This is due to the fact that our planet is revolving around the sun on its fixed orbital plan. Then, as a consequence, we have that the maximum latitude we may consider is 66.5 degrees. So this is because you know that the Earth is not perfectly spheric. Instead, it is an ellipsoid, meaning that it is compressed at its poles, so that the maximum possible latitude corresponding to the Arctic Circle is 66.5 degrees. If we put these two maximum values together, maximum declination and maximum solar declination, maximum latitude, we obtain a quantity that is smaller than 1. As a consequence, we may understand that the photoperiod is also always a quantity that is comprised in the range 0.5, 1, while for higher latitudes, means latitudes whose values are larger than the maximum possible latitude, we consider P, the photoperiod, 1 during summer and 0 during winter. As you know very well, in our, for example, in our hemisphere, boreal hemisphere, you know that at the poles during summer we have 24 hours light, while during winter we have 0 hours light. So that the photoperiod function varies in the interval 0, 1, 0 during summer, 0 during winter at the poles, polar latitudes, and 1 during summers at the polar latitudes. So this is a very trivial model that describes the quantity of radiation that reaches the Earth as a function of the place of the Earth and as a function of the year. If we plot the possible function of the photoperiod as a function of the latitude, we may see that if we made the integral at different latitudes, so let's go from 25 northern degrees of latitude up to 50 degrees latitude, and if we integrate the function that we have defined, we obtain this kind of functions. So here we are representing the quantity of energy per unit surface of a planet reaching the Earth in different periods of year, January, February, March, December, at different latitudes. We may, for example, observe that this function in June and as a maximum value. So in June, you have a maximum photoperiod. In fact, in June, you have what we call the summer solstitium, the longest daylight of the year. Of course, these calculations are made by assuming a mean daily clear sky, short wavelength solar radiation. Of course, depends on the latitude and day of the year, and we are assuming here that the fraction of covered sky, C, is equal to 0. In general, we may say that this type of function are well approximated by extrapolation by a very simple sinusoidal function. So the intensity of light arriving on day n in a certain place of the Earth is equal to A plus B times sinus epsilon, where epsilon, I recall you, is a function of yearly angle. Epsilon, sorry, is the yearly angle, but is a function of the day n, where n equal 1 corresponds to the 1st of March, and A and B are the parameters you may employ to calibrate these irradiation functions depending on the place, so depending on the latitude at which you are modeling the incident radiation on the surface of the planet. Sorry, one moment. Okay, we have said that this function, that is an experimental function, it is obtained by measuring the solar radiation at different latitudes and along all the time of the year, is a function based on the assumption of clear mean daily clear sky short wavelength solar radiation. And it is, for example, evident that if we compare this kind of, if we compare solar irradiation measurement at different places on the surface of the planet, for example, here you have measures in megajoule per square meter per day, measured, for example, in Venice. Each dot here corresponds to a daily 1 day measure of solar radiation. If you do these measures in Venice, or if you do these measures in Manila, you obtain two very different distributions. Why this? Because of course Venice is a northern hemisphere temperate climate zones, while in Manila it is near tropical country, in which we have two clear seasons, two different seasons, but are a sunny seasons and a rainy seasons. Of course, during the rainy seasons in Manila, you have a strong covering of clouds, so that you have a almost fixed incident solar radiation in this period, in which the clouds absorb most of the energy coming from the sun. So you understand that the percentage C of the fraction of the covered sky, it has a significant influence on the model what you shall apply to describe or to model the quantity of solar radiation arriving onto your system, onto your ecosystem. In particular, you may include this effect due to an heterogeneous cloud cover over the year, and for doing this, we shall subdivide the solar radiation arriving onto the planet onto different contributions. For example, we may say that energy flow arriving onto the surface of a planet, so net radiation on the surface. Net radiation means radiation due to short wavelength absorbed by the cloud, minus radiation due to short wavelength reflected by the cloud, plus radiation due to long wavelength absorbed by the cloud, minus radiation due to long wavelength reflected by the clouds, minus the back radiation, or if you want, a black body radiation, QBR, that is a function of the temperature. Then we may express all these terms. We may subdivide these terms. For example, we may calculate the net short wave radiation. So net meaning subtracted the cloud reflection. So what arrives on the surface of planet once radiation it has been reflected by the clouds, and you make the net short wave radiation depending on the cloud covering. Do you remember this factor C? C, it is 0 when we have clear sky, and it is 1 when we have completely covered sky. So C is a percentage of the sky that is covered by clouds. So we have this empirical function that describes the net shortwave radiation. We have the analogous for the long wave emissions from the atmosphere to the surface. Again, C is the fraction of the covered sky. TA is the dry bulb air temperature expressed in Fahrenheit. So it is the temperature of the atmosphere. So it is linked to the effect of absorption by humidity in the atmosphere, while the black reflected radiation may be seen as the heat emission from water in the atmosphere, back radiation, and it is dependent on the Stefan Boltzmann constant and on the temperature of the water in Kelvin degrees. So we have this model that subdivide the contribution to the radiation arrives on the planet in terms so that you may include the effect of the clouds in reducing the quantity of radiation arriving on the surface and coming from the sun. So let's start back, let's give back a little bit. Photoperiod, quantity of day, but we have sun. The photoperiod goes from 1 in summer at the pole, North Pole, to 0 in winter at the North Pole. Of course, for the South Pole, we have the reverse. Then we have a function that tells us as a function of the day of the year and the quantity of solar radiation that arrives on the surface of a planet. So this is watt per square meters, E watt per square meters. Then we can include the effect of clouds by subdividing the contribution to this total to net solar radiation in the short wave and in the long wave due to the cloud covering, subtracting the cloud effect. And if we put all these together, we know that for models with short time scale, like for example a day, we may say that the intensity of the radiation arriving on the my ecosystem as a function of the time of the day, so hours, may be made dependent on the intensity of the radiation En that arrives on during that day, normalized by the photoperiod, multiplied by this function of the time of the day and of the year of the number of the year, sorry, and the number of the day and number of the day of the year and the latitude. Okay, En, I recall you, is the mean daily radiation given from the function that we have seen, A plus B sinus the yearly angle, so this function. Okay, so this is the complete way of describing the effects of solar radiation arriving on the surface of the planet. Why this it is important? Because as we have already said, solar radiation is the fundamental forcing function described that drives the basic production process, what is primary production, through a process of photosynthesis, so that by employing these kind of models, this is the short time scale models, or if you have, for example, a long scale model, like for example, a daily radiation model, you may employ this simple sinusoidal interpoling function. Then by these models, you may estimate the quantity of solar radiation arriving on the surface of the planet. We will see next week how we may employ these quantities in order to estimate the primary production due to photosynthetic processes. So we will have to include some more calibration constants linked to a photosynthetic process. Okay, this more or less ends the topic of evaluating the effect or the quantity of model employed to evaluate the quantity of solar radiation arriving on the surface of a planet. Now we shall give a look to another important biogeochemical cycles by which we have talked in several contexts during this class, that is the nitrogen cycle. Nitrogen cycle pertains to various biogeochemical cycles. We have said that chemical element cycles within ecosystems. For you now, it should be clear that the only meaningful model of chemical, biogeochemical cycles into ecosystems are models that include internal recycling. So the biogeochemical cycle of interest refers to elements that are essential for life. This is why we talk of biogeochemical. These are more or less 30: phosphorus, nitrogen, oxygen, carbon, and then hydrogen, iron, and so on. This is important to include cycling because resources are not unlimited. So recycling is a fundamental aspect of living processes. Cycling through the different media means cycling through land, water, air, and so on. This is why we talk about bio-geo cycling, biogeochemical cycling. And cycling, I recall you that it is sustained by solar energy. So it is the solar energy arriving on the surface of the planet that sustains the cycling of the relevant chemical elements, relevant for life chemical elements through the different geospheres. We have, you may recall that we had a lecture entitled the equilibrium between the four geospheres. So we have already talked of the fact that through the different geospheres, we have transfers of bio-relevant chemical element. In particular, we may start looking at the cycles of what gaseous elements like are, for example, nitrogen. But as I recall you, nitrogen, it is in its gaseous form, it is N2, or oxygen, or other elements that are carbon, for example, CO2. So carbon dioxide, it is a gaseous form of carbon, but cycles through the element, through the various geospheres. So these gaseous storages in the atmosphere play an important role in controlling the cycles. So with the possibility of having atmospheric storages play a relevant role in the capability of being stable or resilient or resistant to perturbation of ecosystems. Question is to what extent an ecosystem is resilient or resistant to perturbation in the concentration of gases. This is an open subject, but it depends on the characteristics of the different elements. We are not going to the details, but you shall take into consideration this aspect when you are modeling a specific, through a specific currency, throughout a specific ecosystems or processes describing ecosystems in different locations. It is important to note that cycles are not only relevant for gaseous elements, but also there is a relevant aspect linked to sedimentary elements. This is of particular relevance for phosphorus, because land, in this case, land meaning the lithosphere is the main storage system for phosphorus. In general, the lithosphere is a little bit less resilient, while the atmosphere or gaseous element is much more resilient. We may start describing solar cycle, biogeochemical cycle, by saying that solar, it is the driving force that induce producers, or producers absorb solar energy. They assimilate inorganic forms of nutrients, and they produce organic form of nutrients that are then passed to consumers. Consumers release organic forms that are then processed by decomposers. Decomposers convert these organic forms into inorganic form, and these inorganic forms are released back to the environment. There is an internal cycle from the atmosphere to the lithosphere to the hydrosphere, as we have seen. So there is a continuous exchange of elements between these four spheres. So this is the hydrosphere, atmosphere, lithosphere, and this is the biosphere part of the story. So we may subdivide according to subdivision we have made into the fourth sphere. Here we have a hydrosphere, the lithosphere, and the hydrosphere, atmosphere, and lithosphere, and here we have the biosphere. So this is a different way of subdividing in terms of processes the contribution of the different spheres to the equilibrium concentration of the various elements. Why we are focusing here on nitrogen cycle, why it is nitrogen cycles relevant? Because nitrogen, we may say, it is in terms of gaseous form, it is a diatomic gas, it is very inert, because you may recall that N2 is a triple, very strong bond. Nitrogen is relevant because it constitutes the largest parts of the air volume, 78%, may be found in a significant quantity in other forms in the Earth crust, significant, but very much less compared to the air. 0.03% of nitrogen is in the Earth crust. Nitrogen displays some very interesting compounds from the biochemical point of view. For example, ammonia, NH4, that comes from bacterial degradation of organic nitrogenous substances. Ammonia, for example, may be found in fertilizers. We have only few primary producers that can exploit gaseous nitrogen, because gaseous nitrogen is a very strong triple covalent bond. The ammonium ion, on the contrary, is much more easily employed, because ammonia is very small, a very small molecule compared, for example, to oxidized forms of nitrogen, like, for example, the nitric acid or nitrate and nitrite. You may find nitrogen in agricultural salts of nitric acids, for example, the nitrate, but also in other salts, like, for example, the sodium nitrate, or the potassium nitrate, or calcium cyanamides, and so on. And also in various forms of nitrite salts of nitrous acids, like NO2 minus. So you find nitrogen in several elements of relevance for the biochemical cycle. Why so nitrogen? Why understanding the nitrogen cycle? It is so important. For one thing, for example, nitrogen is found in the DNA, so it's found in vitamins, it's found in amino acids, in proteins, in chlorophyll. So these are all key molecules for biochemical and ecological processes. So if you want to study ecological processes, nitrogen cycles shall be well understood. Nitrogen is very abundant in the atmosphere, so it is very relevant for the gaseous cycles, but the fixation is very difficult. So transferring gaseous nitrogen, N2, it is a triple covalent bonds, and fixing this gas into, for example, amino acids or proteins requires much more energy. Consequently, nitrogen is often a limiting nutrient for primary production. So this is why when we are looking for nutrient limitation, as we will see next week, nutrient limitation is a very relevant process. As we will see next week, when we deal with nutrient limitation, we shall study the availability of nitrogen for primary production. Some compounds of nitrogen are toxic. Okay, for example, nitrate is toxic. Nitrogen is fundamental for studying processes that may be dystrophic processes like eutrophication. That is relevant processes to be studied, for example, in coastal zones, in order to avoid toxic algal blooms or in order to protect or foster tourism, fisheries, and so on. The nitrogen cycle is a very complex cycle because you may find nitrogen that plays several roles as a function of its oxidation numbers and may vary from -3 in case of ammonia to +5 in the case of nitrate. For example, if we may give a look in terms of biogeochemical processes, here we are mixing all processes of exchange of nitrogen in the various biosphere. So this is a really kind of schematization of the biogeochemical processes of nitrogen exchange. So, for example, you have nitrogen changing from NO2 nitrate onto NO3, so nitrate onto nitrate onto gas of nitrogen. Then you have several processes, for example, process 10 to 11, 10 uptake. So you talk of uptake by, for example, algae of nitrate, or you may talk of fixation by bacteria of gaseous nitrogen by, for example, into phytoplankton or periphyton and so on. So when you have several other processes, like, for example, processes in which you have nitrogen transfer due to respiration processes, like the process 13, which you have respiration. In the process 13, phytoplankton respiration transfer nitrogen from the phytoplanktonic pool into the ammonia pool, into the water, or dissolved in organic forms. Of these forms, you have also forms that are transferred by processes like exudation or by grazing. Grazing is a predation form. Grazing is predation of the zooplankton onto the phytoplanktonic pool. So in order to describe a nitrogen cycle, you shall also understand transfer of nitrogen from these pools. So from the phytoplanktonic pools onto the zooplanktonic pools and so on. In particular, we may depict all the nitrogen processes. This is just repeating of concepts what you already know. Let's start by considering processes involving atmospheric nitrogen. But as we said, it is very abundant, so never limiting. 78% of the atmosphere is nitrogen in the gaseous form. But it is inert because N2 is a triple covalent bond. So before being used by living organism, it has to be it has to be fixed. So the first process involving atmospheric nitrogen is biological fixation that is carried by bacteria, like, for example, blue-green algae, bacteria in symbiosis with plants, for example, legume, roots, and so on. In this case, nitrogen is fixed into organic nitrogen, so gaseous nitrogen 2 has a very stable triple covalent bond, and symbiotic bacteria are needed to break it. So very specified bacteria break these bonds and transfer nitrogen to plants that then absorbs ammonium or nitrate that are soluble based on the fixed ammonium. So you have what we call biological fixation. Biological fixation, because also we have some cases of non-biological fixation, which, for example, in cases of strong energy sources, like, for example, are the case in thunders, in which you have strong energy transfers, you may happen that you have non-biological fixation because these very strong energetic events may break the triple covalent bonds. Then once biological fixation transfer nitrogen from the atmosphere onto the plants, then a subsequent series of very complex biological processes take place. In particular, in the water column, you have ammonia, nitrogen, and H4, or nitrate, or nitrate NO3, nitrate NO2. In this case, you have aqueous forms from the water column by diffusion. These forms of nitrogen are transferred into the sediments. And then you may also include that, for example, predators that, for example, feed on plants or on primary production, transfer nitrogen from the organic forms and the organic form into the inorganic dissolved forms like ammonia or nitrate, or oxidized forms. Of course, nitrogen in organic forms may undergo processes like sedimentation and resuspension. By now, you shall be able to model also these processes because we have introduced the processes describing sedimentation and resuspension. Then we have another important process, that is the reverse process that transfers nitrogen from a water column to the atmosphere, and this process is called volatilization. We have already seen some example of volatilization, in particular when we were discussing the interaction between the atmosphere and the hydrosphere. We said that these processes are modeled by employing Henry constant models or Henry models. We may say that NH4 in the gaseous form plus water converts NH3 in the aqueous form plus water, and then this is converted by biological processes into ammonia in aqueous form plus hydronium. This is called stripping in waters or soils with high pH, for example, water-powered bodies in summers in which pH is increased by photosynthetic production. You have important stripping processes, so processes of conversion of gaseous nitrogen into aqueous ammonia. At low temperature, the reaction slows down. So this process may also be used in wastewater treatment plants with low flows, for example, by adding lime to increase pH. Another relevant process, including nitrogen in organic form, is the so-called mineralization. Mineralization is the conversion of organic forms of nitrogen that are decomposed into ammonium. This normally is carried on by bacteria that degrade nitrogen compounds and incorporate the produced ammonium they need The excess is related as ammonium ions. So the mineralization process is a transfer process from the biosphere into the hydrosphere, generally the hydrosphere, or sometimes the lithosphere by sedimentation. Of course, this process in the hydrosphere uh, drives other processes, but is, for example, the process of nitrification. In nitrification, the ammonium ion is converted into nitrate and then into nitrate. This is done essentially by two bacteria strains, Nitrosomonas, and after that, the Nitrobacter. So Nitrosomonas are responsible for the first step, conversion of ammonia into nitrate, and the Nitrobacter are responsible of converting nitrate into nitrate. These bacteria are chemoautotrophic bacteria, so they use the exothermic reaction of oxidation of ammonium and nitrates, and the energy source comes from nitrates. Sorry, the energy source comes from CO2. So they consume CO2 as a carbon source. Sorry, the energy comes from nitrates and the carbons comes from CO2. So they consume CO2 as a carbon source. The biological process is called nitrification. You may write this process by saying that NH4 plus is converted into NHO2, what is nitrate, that is subsequently converted to NO3. The point is that this process, the first part of the process that is carried by nitrosomonas. So in this case, the first reaction takes, for example, ammonium nitrogen and converts it into nitrate. And we may say that this process is described by an equilibrium constant K1. So here we are saying that the variation in nitrogen pooling the form NH4 in time is equal to equilibrium constant K1 minus K1 times the concentration of nitrogen in the 4NH4. This process then is taken up by Nitrobacter, but convert nitrate by employing some oxygen, gaseous oxygen, converts it into nitrous. You say that in the first part of the process, nitrosomonas, you need oxygen, and in the second part of the process, Nitrobacter, you need oxygen as well. So nitrification, that is maybe split down into sub-processes by Nitrosomonas and Nitrobacter, is a process that requires oxygen. In particular, we may recognize that the two different equilibrium constants, K2 and K1, are very different. In particular, K2 is much larger than K1. This means that ammonia oxidation is the limiting process. But for high temperature, like, as you know, with constancies depends strongly on temperature. For high temperature, this may vary. So there is a high dependencies on the equilibrium constant K1 and K2 on the temperature. The important point is that the limiting process is the first one, and given that, the limiting process is the first one, the K1, because K2 is much bigger. This means that as soon as there is some nitrate, then this is immediately converted to nitrate by Nitrobacter. This is also one of the reasons why it is not very relevant if you are planning a monitoring program to measure the concentration of nitrate, because the concentration of nitrate is immediately converted into nitrate. So it is much more relevant to measure nitrate concentration instead of measuring nitrate concentrations. So if you have a monitoring program and in the monitoring program is included also nitrate concentration measurements, you should be aware of the fact that even if, given that these processes are time consuming and money consuming, maybe it is not so relevant to measure the concentration of nitrate, but instead it is very relevant to measure the concentration of nitrates. There is an important dependence also on the pH for nitrification. So you have an optimum pH value for the nitrification process, but it is in the interval 8 to 9 pH. There is strong dependence on alkalinity. In particular, these two graphs tells you that both for the first part of the process, that is ammonia oxidation, and the second part of the process, that is nitrate oxidation, continuous light and dashed lines, you have a part of an interval of pH, let's say between 8 and 9, which you have a maximum, you reach almost maximum of percent of the rate, the maximum percent rates of transformation. So it is important what you need when you want to control and to evaluate the effect of nitrification, also to control the pH. So you're going, if you, for example, want to evaluate the nitrification process that takes away nitrogen from a water body, then you not only have to control the nitrate concentration, because it is a nitrate, because nitrate is the limiting, nitrate concentration is the limiting process. So you not only have to control the nitrate concentration, instead you also have to control the pH. What are the biological processes in the nitron cycle? Nitrification is for sure the most relevant, in which temperature influences the maximum reaction rate. We have an exponential growth process between 10 to 20 Celsius degree. We have almost constant process rate between 30 and 35 Celsius degree, and we have almost zero reaction between 35 and 40, and absolutely no reaction above 50 Celsius degree. So here you have rules that tells you in terms of temperature what are the in which range of process speeds or process reactions you will find nitrifications. Other limiting factors, of course, are moisture. These are limiting factors for bacterial growth, because bacteria need water to survive. You can include it by monocynetic like, but we will see more closely next week with. Another important process involving nitrogen is denitrification. So it is a reduction process taking place in anoxic condition. So you may recall that nitrification, so the conversion of ammonia to nitrate and nitrate, it is an anoxic process, and it is a process that takes place in presence of oxygen, while denitrification, that is the conversion of nitrate into gaseous nitrogen, it is a process that takes place in anoxic condition. In this case, nitrate acts as an electron acceptor and can be reduced to gaseous nitrogen or to one of the following oxides of nitrogen. The denitrification process is described by these chemical reaction, sorry, let me go back. By denitrification is described by this chemical reaction in which we have NO3 nitrate that reacts together with organic substance. I recall you that in this case you need a carbon source. So this is the organic substance as carbon source. In this case, nitrate and organic substance is converted into water, gaseous nitrogen, and CO2. Process rate increased by the kind of substrate, for example, methanol or sewage waters. Denitrification takes place within a pH 6 to 10. It has an optimum rate between 7.5 and 9 pH. Oxygen inhibits the process. So recall, denitrification is an anoxic process taking place in oxygen lacking conditions. There are other limiting factors, like, for example, the Ks is the semi-saturation constant for this factor, for this process. It is not a problem, of course, in wastewater treatment plants in case in which you have a very strong organic substance content, while sometimes oxygen may be consumed by facultative bacteria to oxidate organic substance. This is an exemplification of why phytodiapuration in wetland system is a relevant process. As I told you already, it is the only relevant process that you may employ in order to treat diffuse pollution. In this case, you have a nitrification or a nitro-denitro cohabitation processes. This process of phytodepuration ability is based on nitrogen oxidation and then oxygen absence. Such contrasting conditions may be found in the roots of common reed phragmites. Generally, sediments do not contain oxygen. Instead, oxygen is brought down by roots of the phragmites or by roots of the reeds. You may say, for example, we may describe this process by saying that the roots transport oxygen, but it is obtained by photosynthesis down into the root system, and it is into the root system that you have the coexistence of the condition, the nitro-denitro coexistence of processes that are responsible of denitrification that might be a relevant process in diffuse pollution treatment. So remember that nitro-denitro conditions depends on the presence of oxygen. So you shall have condition of oxygen presence for oxidation, nitrification, and condition of oxygen absence for denitrification, and typically you find this type of condition in the root zones. What are the key nitrogen removal processes in wetland systems? The first one is nitrification in the rhizosphere, bacterial films, oxidized sediments zone. Then you have denitrification in the bottom area, in which you do not have oxygen. Then you have ammonia volatilization, but this is a process that is strongly controlled by pH. So you have ammonia volatilization only in high pH conditions, so pH larger than 8. And plant uptake, so this is ammonia transfer from water and soils into into the biosphere. And then you have barriers, so interactions, between the water column and the sediments. So you have ammonia that is buried into the deep root zone. And these processes are strongly controlled by ion exchange. I call you that in the case of ammonia volatilization, we have already seen a model, for example, the Whitman two films surface process that is responsible of transferring ammonia from the hydrosphere into the atmosphere, and this is ammonia volatilization. Another relevant process that governs the transfer of nitrogen oxides from the atmosphere into the biosphere is atmospheric deposition. Biosphere-atmosphere exchange may be also driven by exchange combustion and vice versa. You may have dry deposition. And also you may recall that Goldie in 1990 described deposition alone, but can lead to higher than European community limits for drinkable water. So you have to be aware of the fact that nitrogen oxides atmospheric deposition may be a relevant process for what may change the water quality conditions or surface water body quality condition. To resume, what are the processes involved in nitrogen fixation? In the nitrogen cycle, nitrogen fixation that is conducted by soil microorganisms in symbiosis with some plants, for example, legumes, that fix atmospheric nitrogen and transform it into organic nitrogen. When we have nitrogen accumulation, typically bacterial uptake. So this is bacteria that are feeding on various forms of nitrogens, and these forms may be nitrate or ammonia. So you may have heterotrophic soil organisms that convert ammonia to organic compounds. This is uptake proteins. Or you may have sorry, one moment. Pronto?
Corriere Bartolini, Palmieri.
Le apro.
Sono qua fuori.
Apro il cancello, l'ha visto? Mi mette il pacco là sopra?
Sì, ti ho messo sopra la muleta.
Bravissimo, grazie.
Ciao.
I'm sorry, I received an important courier notification. Sorry. We were saying the processes of a nitrogen cycle, nitrogen fixation, nitrogen accumulation. Then we have ammonification, so it is decomposition of proteins and other forms of organic nitrogen into ammonium. Then we have nitrification, so oxidation of ammonium into nitrite and nitrate. Denitrification, conversion of ammonia nitrate into gaseous nitrogen, and then ammonia volatilization, so the transfer of ammonia into the atmosphere. To conclude this lecture, we shall give a look to the bioavailable forms of nitrogen. We may subdivide these in organic and inorganic forms. Organic dissolved, organic may be dissolved or particulate. Inorganic may be, for example, ammonia that is dissolved, or nitrate and nitrate that are dissolved forms. Organic forms of nitrogen may be dissolved or particulate, as we said, but it is important to note that these are the bioavailable forms. So organic nitrogen may be found bioavailable in dissolved forms. So this is organic dissolved organic nitrogen, sometimes called DON, or particulated organic nitrogen, sometimes called PON, but the most available forms are the inorganic ammonia or nitrate. Please, of the ammonia and nitrate forms, remember that the most available is, of course, ammonia, because it's smaller than nitrate. If you are a phytoplankton cell and you are to choose which nitrogen form to feed on, and you have a choice to choose between nitrate and between ammonia, then you will firstly choose ammonia, because ammonia is smaller, so it passes more easily the cell membranes, so it is more easily assimilated or embodied into the phytoplankton cells. Okay, we stop here by now, and now I stay here. And I wait for your questions. Otherwise, we shall go to the next